In the world of manufacturing, there's this one huge challenge that honestly makes almost everything around us even possible, and it all comes down to achieving the perfect grip.
So let's just dive right in. I want you to picture something, a big, solid bar of steel, and it's spinning at thousands of RPMs. Now at the same time, you're trying to carve into it with an incredibly hard cutting tool. The question, and it's a huge one, is this: how in the world do you hold on to that thing without it, flying across the room?
Well, the answer is pretty cool, actually. You use what I can only describe as some of the most clever and powerful hands ever invented. And no, we're not talking about hands made of flesh and bone. We're talking hardened steel, engineered for just incredible strength and pinpoint precision. These are called work-holding devices, and they are truly the unsung heroes of any modern workshop.
All right, so let's get to know the most common of these powerful mechanical hands. We're going to kick things off by talking about chucks. So what is a chuck? Well, think of it like a super specialized rotating vise. That's really the best way to picture it. Its entire job is to grab onto a part with just immense pressure. It can either squeeze it from the outside in or maybe even expand from the inside out. The goal is always the same, though. Hold that thing absolutely rock solid while the machine does its thing.
Okay, but here's the thing. Not all chucks are created equal, not by a long shot. In the world of lathes and turning, there are two big players that really reign supreme. You've got the speedy, convenient 3-jaw chuck, and then you have the incredibly precise and versatile 4-jaw chuck. And here they are, side by side. You can see the difference right away. With a 3-jaw, see how those jaws are all linked? They move in and out together, all in perfect sync. But with a 4-jaw, each one moves totally on its own, completely independent. And that one single difference, well, it creates this really fascinating trade-off between sheer speed and absolute pinpoint precision.
So what you're looking at here is a classic engineering choice. On one side, you have the 3-jaw, which is self-centering. That means you just tighten one spot and bam, all 3 jaws close in at the same time. This makes it super fast, right? It's perfect if you're making hundreds of identical round parts, like a simple shaft or something. But there's always a but. That speed comes at a price. It can't hold square parts, and its accuracy can kind of drift a bit over time. Now the 4-jaw, yeah, it's slower to set up, but that's actually its superpower. Because the jaws are independent, you can meticulously center a square block for a one-off custom part. You can even mount something intentionally off-center, maybe to create a cam for an engine. It really is a choice between precision and pace.
And check this out. This is another really clever bit of design, especially with the 3-jaw chucks. See those jaws? They're reversible. So you can set them up one way, with the steps facing inward, to grab the outside of a solid bar. But then, you can literally take them out, flip them around, and use the other set of steps to expand and grip the inside of something hollow, like a pipe. It's just a brilliantly simple and effective system.
All right, so we've got round parts covered, hexagonal parts too, but what about all the weird stuff? The awkward, asymmetrical pieces, the parts that just do not want to be held easily. What do you do then? Well, this is exactly where that 4-jaw independent chuck really shines. Since you can move each jaw by itself, it can adapt and clamp down securely on things with flat sides or even lumpy, uneven castings. That's something a 3-jaw, with its self-centering design, just has no way of doing.
Okay, but what if a part is really weird? I mean, truly irregular. Think about something like a pump housing or some other super complex casting. For a job like that, you got to bring out the heavy hitter, the faceplate. Just picture a big, flat disc with a bunch of slots in it. You can bolt your part directly to it using all sorts of custom clamps, blocks, even counterweights. It gives you practically infinite options for holding the absolute most complex shapes you can imagine. Okay, so we've kind of solved the problem of shape, but now let's tackle a whole new problem, length. Imagine you're trying to machine a really long, skinny axle. The force from the cutting tool alone is going to make it bend in the middle or vibrate like a guitar string. It would totally ruin the finish. So, how do you stop that from happening?
The basic solution is actually beautifully simple. What you do is you support the part at both ends, not just in the chuck, but between two special cone-shaped points. We call these centers. You've got one in the spinning part of the machine, the headstock, and another one at the opposite end, in the tailstock, which doesn't move. This setup creates this perfectly rigid axis for the part to spin on, giving it maximum stability.
Now that's a fantastic start, but what if the part is just so long and skinny that it still wants to sag or chatter right in the middle, even when you're holding it between centers? Well then, you need a little extra help. You need a helping hand.
And that helping hand is exactly what a steady rest is. It's basically a ring with these little adjustable supports, and you clamp it right onto the main bed of the lathe. It acts like a fixed third hand, just sitting there, supporting the part at a critical spot to stop any of that bending or vibration while you're cutting.
So the follower rest takes that same idea and kicks it up a notch. Instead of just being clamped in one spot, this thing actually attaches to the machine's carriage. That's the part that moves and carries the cutting tool. And what that means is it travels with the tool, providing support right at the exact point where the cutting is happening. This is absolutely crucial if you're trying to machine a long, thin shaft and you need the diameter to be perfectly consistent from one end to the other.
All right, time to switch gears. Let's do a quick lightning round. We've covered the big workhorses. Now let's talk about the specialists. These are the tools designed for super high precision and really specific jobs.
First up, the collet chuck. When you need extreme accuracy and a grip that's both firm and gentle, especially on smaller parts, this is what you reach for. It's basically a slotted sleeve that squeezes down on the workpiece with perfectly even pressure all the way around.
So think about it. A normal chuck only grabs the part at 3 or 4 points. A collet, on the other hand, grips it along its entire surface, and the result of that is just exceptional concentricity. That's a fancy way of saying the part spins with pretty much zero wobble, and that's essential for really delicate stuff like medical implants or the tiny, tiny gears you'd find inside a wristwatch.
Okay, next challenge. How do you machine the outside of something that's already hollow? Let's say a bearing sleeve. You can't just grip the outside, right? You'd mess up the finish. The answer here is a mandrel.
A mandrel is just a super precise shaft that you slide right inside the hole of your part. It fits in there nice and snug. Then you take that whole assembly and mount it between centers, just like we talked about before. This lets you machine the entire outside surface in one single operation, which guarantees it's perfectly concentric with the inside hole. That's absolutely critical for something like a gear that has to spin perfectly true.
And last up, for the really, really delicate stuff, what if your part is made of steel, but it's just too thin or too fragile to be squeezed by any kind of mechanical jaws? Well, then you turn to the power of magnetism. A magnetic chuck uses a powerful electromagnetic field to hold the workpiece down, perfectly flat and totally secure, without a single clamp in sight.
So after all that, why does any of this matter? Well, think about the precisely machined metal case of the phone that's probably in your pocket right now. Or think about the perfectly balanced turbine blades in a jet engine, soaring through the sky. The truth is, the modern world as we know it is literally built on the foundation of an unshakable grip. All these clever devices, they're the invisible bedrock of all modern manufacturing. So here's my challenge to you. The next time you look at any precision-made object, just take a second and think about how it was held. I wonder, what will you see differently now?